Let me ask you something. You need to train a binary image classifier. What would be your design choice? Would you go for a vision transformer, state of the art, fancy, or a boring old CNN? Now, there are a few constraints. You do not have a massive dataset, and you don't have unlimited compute either. Now, at this point, what would you actually reach for? Vision transformer or CNNs? Most people I actually talk to, including the past me, would go for vision transformer. And now I actually get why. But in practice, that choice often backfires. So, this video is not a vision transformer tutorial. See, I'm not going to show you or explain how attention works or how softmax works. What I'm going to show you in this video is much more useful. The main part or motive of this video is what happens when you take research grade architecture and actually try to use it in a realistic setup. I'll briefly show you what I built, how I trained it, and then we'll spend most of the time on the real question. Why a vision transformer trained from scratch underperforms on small vision tasks and why CNNs still dominate. Now, if you're someone who spends a lot of time reading papers, builds model, and is tired of architecture hype, this video would make sense. So now let me give you some context so that we both are in the same page. So vision transformers were introduced by Google Research. In this particular landmark paper, an image is worth 16 by 16 words. This is a long paper. I won't be explaining the whole paper. I would be just giving you the gist of what this paper includes. Now, as you can see, this is a particular image. Now, this image is cut down or chopped down into patches, and these patches are linearly projected and flattened, and they go into the transformer encoder, which further go into the multi-layer perceptron and then to the classification layer. Okay, so now let us understand how do these vision transformer actually patch up images. So here I have an image. Let's assume this image is 128 pixels wide and 128 pixels in height. So its effective dimension would be 128 cross 128 cross 3. Now, what I want to do is I want to patch this image into 16 by 16 pixels. So here I have divided this image into a 16 by 16 patch. Each individual patch has a dimension of 16 cross 16 cross 16. 16 height, 16 width, and 3 would be the channel. Now, we take a look at a final image after we have patched the image and converted it into patches. Now, here we will be multiplying number of patches into the patch shape. The patch shape is simple, 16 cross 16 cross 3. We have calculated this patch shape here. Now, to calculate the number of patches, we would be first multiplying 128 cross 128, which is the dimension of the original image, and dividing it by the dimensions of a patch, 16 cross 16. So by this math, we get 64 as our number of patches. And we would do some further calculation here, and we would flatten these particular patches by multiplying 16 cross 16 cross 3, which comes out to be 768. So this is our effective dimension, which would be going for further processing. So now we have actually calculated our final image, which is in the shape 64 cross 768. Now we would be adding an extra dimension that would ease up the calculations a bit. Now we have our final tensor 1 cross 64 cross 768. We would be now initializing a weight matrix. Weight matrix could be a linear layer, or you could also initialize by nn dot parameter. So we would be passing this tensor into this weight matrix, and we would be getting a final tensor of shape 1 cross 64 cross 768. Now these would be the patch embeddings. Now take notice, this particular part 768 was pixels, but this is embeddings. Now once we have our patch embeddings ready, we are finally ready to add the CLS token or the classification token. This token is necessary because this token actually is used for classification. So we would be initializing a classification token of dimension 1 cross 768, and we would be concatenating this token in this particular patch embeddings. So this 1 cross 64 cross 768 becomes 1 cross 65 cross 768. So this is the actual part where the CLS token gets added. Now, after we have added the CLS token to our initial tensor, we get a new tensor of shape 1 cross 65 cross 768. Now, we would be initializing a new weight matrix of shape 65 cross 768. And we would be adding this particular weight matrix to our initial tensor, which was this particular tensor. And now, after adding both of them, we have our final embeddings, which is ready to pass into the transformer or attention layers. So now we have our final patch embeddings, which have positional knowledge and basic embedding structure. Now we would be passing these patch embeddings into our transformer encoder. Now this is only one transformer head, but in practice we have multiple transformer heads stacked in linear order. So I won't be going into the nitty-gritty of attention, multi-head attention. Just assume that we would be passing these patch embeddings and we would be getting contextually aware embeddings after the end of this particular cycle. Now these embeddings would be particularly useful in our classification task. After the attention part is complete, we have our final contextually aware embeddings. These are our contextually aware embeddings, which we get by passing through the transformer head. Now, what we would do is we would split these embeddings into first the original embedding, and this is the classification token embedding. Now, we would be just using this particular classification token to perform our classification task. So this token is of dimension 1 cross 768. We would just be using this particular dimensions of it, and we would be passing it through a multi-layer perceptron head. Now this head is of 768 cross number of classes. Now number of classes is the number of output classes that you want. So let's say I have a binary classification task of maybe classification of cat and dogs. So I would actually take two classes because one is cat, one is dog. Similarly, if I want to classify 10 objects, I would use the classification or number of classes as 10. So now after we project this particular tensor into this weight matrix, we would be getting a similar tensor, but it would be of shape 1 comma n classes. So now we are actually ready to dive deep into the code and the implementation. So here I am using the dog versus cats dataset for binary classification task. So I've imported it, some pre-processing, and I would be resizing all these images into 128 cross 128 for, uniformness. I've defined the data loader and the dataset, and this is the main part. This is the first class patch and positional embedding. I have explained this in the previous sections of this video. This is the self-attention part. This is the multi-layer perceptron part. This whole thing, multi-head attention and MLP, these make up the encoder block. Now in this part, I have concatenated all these classes and made a single vision transformer model out of it. Now I would be actually linking this code in the description of this video. You could actually take a look at it and even run all these experiments yourself. Now, this is where I have moved my model to the GPU. You could see the model architecture here. This is the training loop with 10 epochs and a learning rate of 0.001. And I'm using AdamW, which is the go-to optimizer for training any kind of LLM. Now, take a look at the results. Here I have 10 epochs, and you could see the loss actually drops in the first few epochs, then it levels off to 0.67. And same with the accuracy, it improves in the first few epochs, but it stays stuck in 55-ish range. So, what is the reason for it? So, in this use case, why did vision transformers actually fail? And why could CNNs perform better? So, let us understand. So, for vision transformer, we have a lot of parameters. So, it's a better idea to first pre-train the model and then fine-tune it on the particular dataset. And also, they need a tremendous amount of dataset, like millions of images. But for CNNs, you don't need any pre-training. You could just define the model and train it, and it would converge faster and reliably. Now, one more thing is that vision transformers lack inductive bias. They have attention, which attends to all the patches globally, while CNNs are more local. So you could say they actually have a bias. They are specially made for images. Now, vision transformers also, since they have a lot of parameters, they need a lot of compute. While CNNs, they don't need this much compute. So, are vision transformers actually that bad? Well, no. If you pre-train the vision transformer on a very diverse data set, and then you fine-tune this vision transformer on this particular cat versus dog data set, it would actually perform better than the CNN. But since in this use case, I did not pre-train the vision transformer, it performed very bad than a CNN. Now, my vision transformer got like 55% accuracy, but a CNN would have easily crossed 90 to 95% accuracy. In this video, we saw how a vision transformer, a state-of-the-art model, could underperform a CNN. So this states that you should actually use the model which is better for your use case instead of chasing hype. Now, if this video was helpful, please like, share, and subscribe, and see you in the next one.